Hi there. In this video, we'll discuss the topic about finding the average value of a function. So the driving question here is, how do we compute the average value of some certain function on some certain interval? And to illustrate what that means, let me just draw a picture of a function. Okay, so here's some random curve, which we'll call f of x. All right, and a represents the starting point of the interval. B represents the ending point of that interval. And if you think of this as a collection of sand, all right, so let me just kind of shade this in. So imagine walking up on, I use the example of an ant farm. You walk up on a little ant farm enclosed in a rectangular piece of glass, let's say. And if you were to then shake the glass to sort of even out and level out the sand, can you picture in your mind where the level would be? Certainly this level looks too low, and this level looks too high. The level of the sand has got to be somewhere in between, and maybe it's approximately there, although no one could blame you if you thought maybe the level was there. All right, and that's what we call, wherever that level is, that's what we call the average value of the function. Okay, and we're interested in outputs. This output is lower than everything else. This output is higher than everything else. But somewhere there's an average. Okay, and our task is to figure out how to use math to find that average. All right, so let's discuss that. This discussion makes a lot of sense in the context of problems around speed and distance. So let's look at two scenarios. In scenario one, you're driving at 50 miles an hour for this period of time, and then at 60 for this period of time. What's your average speed? We'll also look at a more complex scenario in which your velocity is a variable that's given by this formula. How do you do average speed in that more complex instance? Okay, let's try to answer both questions and see how they're connected. In scenario A, we can just treat this as a real straightforward and simple problem that from 2 o'clock to 3 o'clock, which is a 1-hour interval, we're driving at 50 miles an hour. And if we multiply the speed by the time, we see that you drove, obviously, 50 miles during that time period. Whereas from 3 to 6, a 3-hour time period, we drove at 60 miles an hour. So driving at 60 miles an hour for 3 hours rather, uh, clearly you would drive 180 miles altogether. And so during the entire time interval, starting at 2 and ending at 6, altogether, you can see that you would have driven 230 miles. And since that took 4 hours altogether, we see that the average speed is 57.5 miles per hour. All right, so notice in particular, during the early part of the trip, you were driving slower than that. During the later part of the trip, you were driving faster than that. And you should think about why this is closer to 60 than 50, and that should make sense to you. So meditate on that. Anyway, simple and straightforward math. Scenario B, not so simple and straightforward, but let's make an effort to understand it anyway. What is this saying, first of all, that the velocity at time t is t squared? Well, let's stop and think. This is telling us that if we input a time value, let's say 1 p.m., 2 p.m., 3 p.m., 4 p.m., the speed that we're driving at that particular time is simply the square of that time value. So we'll write 1 squared, 2 squared, 3 squared, 4 squared. Okay. And if we begin to sketch a graph, you may find it helpful to think graphically in this context. If we begin to sketch a graph, we'll have, let me just jot down my time values. Okay. We have 1 mile per hour, 4 miles per hour, 9 miles per hour, and 16 miles per hour. And so the velocity curve looks something like that. Okay, our task is to find the average speed. Again, this would be too small, this would be too large. Somewhere there's an average, somewhere in the middle here. But our task is to find precisely where that middle value is. Okay, and the way in which we can connect that with scenario A is, let's just pretend for a moment that you are actually driving the same speed from 1 p.m. to 2 p.m. In particular, imagine that you kept driving 1 mile per hour. Well, clearly, you would drive 1 mile. If you stayed at that same speed of 4 miles per hour from 2 to 3, you would drive 4 miles. So we've got 1 mile in the first hour, 4 miles in the second hour. And then if you stayed at that speed 9 miles per hour from 3 to 4 p.m., you would, of course, drive 9 miles. All right, so in this scenario in which we've set the speed constant, that makes altogether 14 miles. Okay, and that happened over a 3-hour time interval. So let me just jot down a note. 14 miles were covered in 3 hours. And so what does that work out to as an average? 4.67 miles per hour. Okay, and that estimate, again, was based on setting the speed constant for a full hour. But in reality, the speed varied. It got faster from 1 p.m. to 2 p.m. and didn't stay the same. So if we want to improve our estimate of how far we traveled, we could perhaps use half-hour time intervals. So let me just erase these guys right here. So it's now 1:30, and we can figure out how far we traveled in half an hour. We could do that. I'm not actually going to do it. 3:30, we could estimate. If we set the speed constant from 3:30 to 4, we get a distance traveled. And now we have 6 rectangles, and we could get a closer estimate to the true average speed, to the true distance traveled, and then to the true average speed. And you can see that if you repeat this process, let's say 10,000 times, or even 10 million, okay, to where we're letting the number of rectangles approach infinity, then we're getting the actual distance traveled by looking at the area under this curve. Okay, so in fact what we're doing is we're looking at an integral of this velocity curve, which begins at 1 p.m. and ends at 4 p.m. Okay, so at this point in your calculus studies, you would need to use technology to compute that integral, and so that's what we'll do. Sneak preview, pretty soon we'll learn how to do that using simple algebra tools, but that lesson is yet to come. All right, so we're going to enter in our velocity function t squared, or x squared. We're going to go to the window and set it up so that we start at 1 p.m. and end at 4 p.m. And under the zoom menu, if you scroll down to zoom 0, you'll see the option zoom fit. And that simply allows us, there we go, zoom 0, simply allows us to fit the entire graph into our viewing window in that way. If we pop over to our calculate menu, second trace, you see that option 7 is the integral option. So we'll select option 7, and it needs 2 inputs, a lower limit to calculate, which is 1 p.m., and an upper limit, which is 4 p.m. And it's kind of cool to watch as your calculator generates many, many small rectangles and produces an area under the curve, and apparently the area is 21. So the interpretation there is that for this problem, and can I just highlight to make this next part clear? Let's see here. The area underneath that curve from 1 p.m. to 4 p.m. is 21. That's what that represents. Okay, so let me come over here where we have some room to operate. So the value of the integral is 21. which tells us that you would move 21 miles, if that's our unit of measure. And again, it took 3 hours. Let me just clean this up real quick. By estimate. From 1 p.m. to 4 p.m., that's a 3-hour time interval. And so we can take the distance traveled, divide by the time, and we see that the actual average speed is in fact 7 miles per hour. And let's just quickly compare that to the estimate we produced earlier. All right, so that was quite a bit too low. But again, that was very crude and only based on 3 rectangles. I bet if we did it based on 6 rectangles, we'd get a much better estimate. Okay, true answer. Your average speed for that trip was 7 miles per hour. Okay, now let's head back over to our screen where we have the general question on finding the average value of any function on any interval. Okay, so that speed example was designed just to help you get your mind around what's going on. But there are many functions out there other than distance functions and other than speed functions. So if you're interested in just finding the average value of any function, we can use the procedure that we just applied in this way. Average value is found by taking the area under the curve. Okay, so we want to get this area of this region right in here. Boom. All right, we take the area and divide by the width. Okay, again, the average value of the function is a particular height. Since we're graphing outputs as height, we're looking for really the average height of that curve, if you want to think of it that way. Okay, so there's the concept. The area we know is an integral. So we'll put f of x dx or f of t dt, doesn't matter. I should be consistent though. F of x dx. We're going to start at A, we're going to end at B. In the example problem, we start at 1 p.m. and at 4 p.m. That's a difference of 3 hours. 4 minus 1 is 3. In general, the width of the interval is the difference between B and A. All right, so we'll take that value of the integral, which gives us the area. We'll divide it by the width of the interval, and the answer will represent the average height of the curve or the average value of the function. Why don't we just quickly do an example where we simply apply that and see what we get. So let's take g of t equals sine t. Looking at the sine graph. Okay, here's a quick picture of the sine graph on the interval from 0 to 2 pi. Okay, so the sine function, of course, is just a wave like that. Okie doke. So let's compute the average height. Let's do a couple problems here. Let's look at the average height on the interval from 0 to pi, and then find the average height, average value on the interval from 0 to 2 pi. All right, so in this first interval, we're picturing lots of outputs, lots of heights, and we want the average. Okay, let's begin just conceptually here. The tallest height is 1. The smallest height is 0. So you expect the average height to be somewhere between 0 and 1. And maybe your first guess is a half. Maybe you can do better with your guessing, but that's certainly a reasonable place to start. Okay, so let's go ahead and compute now using the formula. Let's compute the average value on 0 pi. So average value of g on the interval starting at 0, ending at pi. We need to find the integral of sine t dt. Start at 0, end at pi. And we'll subtract b minus a and see what we get. All right, here goes. And I would encourage you, if you're watching this at home, pause the video, work this out yourself, and then continue and hit play. Sine t, we want to start at 0. We want to go to pi in this example. Zoom fit, which is zoom 0. We'll hit second trace, option 7. Lower limit 0, upper limit pi. And we learned that the area, surprisingly and shockingly, is the whole number 2. Who would have thought that would be such a nice, pretty whole number? All right, so that tells us the integral, the area under the curve, is 2. The time interval, pi take away 0, is pi. And so the average value is pi divided by 2. Or sorry, did I say that the right way? No. 2 divided by pi, rather. 2 divided by pi is approximately 0.636. Okay, so does that square with our intuition? Is it believable that the average value is 0.636? Looks pretty reasonable that that's the average height on that particular interval. Okay, let's do one further example in which we compute the average value, and I'll just modify this real quickly. On the interval from 0 to 2 pi, so that would make these changes. Now we're looking at 2 pi everywhere. And so now we're going to have to recalculate the integral. Since we've got a new interval, let's go ahead and calculate it. But before I do that, can you make a prediction? Can you just sort of use your common sense here? Looking at these arrows, okay, what do you think is the average height of the curve? Well, let's find out. Take a guess, and then we'll check it. Okay, this time we're going to go all the way to 2 pi. Oops. 2 pi. Zoom fit again. Okay, we see the full wave, one full period. Second trace 7 gives us an integral. Lower limit 0, upper limit 2 pi. Whoops, did I type something in wrong there? I don't think it's recognizing what I want it to do. So let me just go back here and increase this to 6.3. All right, I got errored out there. Zoom 0. If you try to go even like a millionth past the interval, then it gives you an error. So let's try that again. Second trace 7, lower limit 0, upper limit 2 pi. And we can see the value of the integral is 0. Now that's interesting. Can you see why that's 0? That is something to think about. Okay, so let me make my changes here. And I'll make the changes in red so you can see the difference there. The value of the integral is 0. And when we divide, we're getting 0. So apparently the average value is 0. Challenge, can you make sense of that intuitively? See if you can understand how it is exactly that the average value of the sine function on this interval is 0. Okay, I hope you found this video helpful in understanding the concept of average value of a function. We'll see you next time.